Start recording here. So we have one more problem to do from this old section, and from 8.3. So this is still 8.3 continued. And that is, we are going to solve the initial value problem. The square root of x squared minus 9 dy dx is equal to 1, and we are told that y of 5 is equal to the natural log of 3. So basically we're given a problem, and somehow we have to find y, and then we're also told, hey, when you plug 5 into your y equation, you end up getting the natural log of 3. And so the first thing is we have to worry about trying to solve the equation y. So this is actually a very I don't really want to say easy, but in terms of this problem, there are problems that show up in the course differential equations. So if you've heard of differential equations, so differential equations is basically you're solving equations that have derivatives in them. And so that's what I have here, right? I have an equation that has a derivative in it, and so I'm trying to find the formula, the y, that makes this that I can solve for this. This one was not given to us in like a nice form. So this is actually what's called a separable differential equation. And so separable differential equations are kind of like the most straightforward, the easiest type of differential equation. They're the kind you first learn, like usually the very first thing you learn in differential equations. And so the reason that they're called separable is because I can separate and get all the stuff that deals with y on one side and all the stuff that deals with x on the other side. So that is the first thing that we're going to do. So we are going to separate this out and get everything that has an x on one side and everything that has a y on the other side. So the first thing that I'm essentially going to do is, and again, it's kind of this abusive notation that we do, but I have a dy over dx, and I can think of these, it says 8.3, and then it says like CON apostrophe T, so like abbreviated continued. Like, so it's just saying I'm continuing this stuff from 8.3. Yeah, no problem. So I'm going to abuse this notation, right? And we're going to think of these as kind of two separate pieces, just like we've done before. And so the very first thing I'm going to do is I'm going to multiply up both sides by dx. So if I do that, I end up with the square root of x squared minus 9 dy is equal to 1 times dx. So 1 dx. Right, so I'm basically just trying to get the y stuff all by itself. The only y thing we have is dy, and then I'm trying to get all the x stuff by itself on the other side. So the next thing to do is to notice that here I have the square root of x squared minus 9. And so what I can do is I can divide both sides by the square root of x squared minus 9. So we're going to end up with dy is equal to dx over the square root of x squared minus 9. And so now I have, I basically have separated my variables. I have all the x's on one side and all the y's on the other side. So questions about what I did so far? No. Okay, so in separating the variables and solving differential equations this way, the next thing that you do is you end up integrating both sides. So if I integrate this side and I integrate this side, so this is kind of nice because the integral of dy would be what? y, right. So on the left-hand side, I end up with y, and on the right-hand side, I have this ugly integral, which is going to take us a little bit more work to figure out, right? So I need to figure out the integral of dx over the square root of x squared minus 9. I should say that initial value problems and the separation of variables, it is not dependent. It's not like, oh, you can only do this with trig substitution. You can do it with any equation. You could do it where it turned out to give you just a trig integral, or you could do it where you turned out to have to use integration by parts. It's just, I pull it in here now, just because it's kind of a nice little problem. But it's not tied to trig substitution. So just to make that kind of clear. But now we do have a trig substitution problem. And so if I look at this, right, what substitution am I going to make? So remember, I have down there an x squared minus a squared. Right, so we're going to do a secant theta. So we're going to let x be equal to a secant theta. And then that means that dx, and so, oops, I should have said, in this case, our a is what? I shouldn't write a, I should write what it is. Yeah, our a is a 3, so it should be 3 secant theta. And so our dx is going to be 3 secant theta tangent theta, d theta. And then I also have to figure out the square root of x squared minus 9. So that's going to be the square root of 3 secant squared theta. Oops. Should be careful how I write this here. 3 secant theta squared minus 9. So that's going to be the square root of 9 secant squared theta minus 9. So the square root of 9 times secant squared theta minus 1. And secant squared theta minus 1 is tangent squared theta. So we have the square root of 9 tangent squared theta, which is just 3 tangent theta. I know I got a little down on the page here. And then also from the 3 secant theta, right? So x equals 3 secant theta, I'm going to make my triangle. So divide both sides by 3. So the secant of theta equals x over 3. So here's theta. Remember, secant is the hypotenuse over the opposite. And then that makes this side, we would end up with x squared minus 9 if you do the Pythagorean theorem out. Questions about any of that so far? No. Oh, yeah, you're right. I was trying to stick it on here quickly. Thank you. Secant is hypotenuse over adjacent, and so it's this side that's x squared minus 9. Thank you. Sorry about that. Other questions? No. It's Thursday, right? I get a pass because it's Thursday. End of the week. Okay. So now I'm at a point where I can plug into my integral, right? So here's my integral. So I'm going to come up here. So y is going to be equal to the integral. So dx is 3 secant theta tangent theta d theta. And then that square root in the bottom is just 3 tangent theta. And so that's pretty nice because my 3's would cancel, my secant thetas, or my tangent thetas cancel, and I'm just left with the integral of secant theta, d theta. And the integral of secant theta is one of the ones that I have on that sheet for you, right? So this ends up being just the natural log of secant theta plus tangent theta plus c. And then I just have to pick off from my triangle what's the secant theta, what's the tangent theta. So y ends up being the natural log of the absolute value. So the secant of theta is x over 3. And the tangent of theta is the opposite, square root of x squared minus 9 over the adjacent 3 plus c. So far the only difference between the problems we were solving last class and this problem is at the beginning we had to work a little bit to get it into a form where we could just do what we were doing last class and solve the integral. Questions about the integral, anything I have up there right now, because there is another step that we're going to do. Okay, so if you notice at the beginning of the problem, they told us that y of 5 is equal to the natural log of 3. And I haven't used that information yet. So what that information is going to do is it's actually going to allow me to figure out what the value of c for this problem is. So we know that y of 5 equals the natural log of 3. So if I plug that into what I just found for y, we're saying the natural log of 3 is equal to the natural log of 5 divided by 3 plus the square root of 5 squared minus 9, all divided by 3, plus c. So we end up with the natural log of 3 is equal to the natural log of 5/3 plus 5 squared is 25. 25 minus 9 is 16. Square root of 16 is 4. So 5/3 plus 4/3 plus c. So the natural log of 3 is equal to the natural log of 9/3 plus c. So 9/3 is 3, right? So we end up with natural log of 3 equals natural log of 3 plus c. So in this case, c turns out to be equal to 0. Not always the case. C could be 0, c could be 1, c could be 15, negative 47, doesn't matter. It could be any number. But in this case, c turns out to be 0. So our final answer is that our function that solves this equation is y equals the natural log of the absolute value of x over 3 plus the square root of x squared minus 9 all over 3. Questions?
Real quick, I don't, so since you already got the equation, why did we have to plug in if we had already gotten that equation?
Because, so you're saying, like, since it's the same thing I have up here?
Yeah.
Okay, it's because I have to find C. Up here, I don't know what C is. You know, if this wasn't a 3, if this had been like the natural log of, like, say, 7, right? Then I would have had down here, natural log of 7 equals natural log of 3 plus C. So I would have subtracted the natural log of 7, and my C would have ended up being natural log of 7 minus the natural log of 3. So it's because it's dependent on, you're trying to actually find a specific value for C.
Okay.
So in this case, I found that specific value for C ended up being 0, but it didn't have to be. It could have been some other number.
And that's why we took it off in our final answer, because it would end up just adding 0.
Yeah, I took it off the final answer because it was just, you were adding 0. Yep.
Okay, thank you.
No problem. Other questions?
Dr. Gorman, just really quickly. So, the last part you did from the line that says y equals 5 equals natural log of 3, from there down, that only applies when we're doing initial value problems?
Yeah, when they give you that information. So they're going to have to give you that information. They're going to have to tell you, like, y of something is equal to some other value.
Oh, okay. Thank you.
No problem. Other questions? No. Okay, so that was the end of section 8.3. So now we're actually going to do section 8.5. So we're going to spend the rest of the day doing 8.5. We probably won't get through all of 8.5 today. We probably will need some of next class, so on Tuesday, to finish section 8.5 here. I'm just going to pull this up so I don't accidentally move the page. So section 8.5 is integration using partial fractions. Okay, so I'm going to talk just first kind of a little bit about partial fractions. Like, what is partial fractions? What are we trying to do? Why is it helpful? And then we'll get into the nitty gritty of, like, how do we actually do partial fractions? And then we'll actually do a bunch of examples. So if you were given this integral, so the integral of 5x minus 7 over x squared minus 3x plus 2 dx. So, it's a pretty nice little integral, right? The problem is like, if you went to integrate it, you probably would be like, oh, all right, I'll let u be x squared minus 3x plus 2. That kind of makes sense. But you would quickly find, if you did that, if you tried letting u be equal to x squared minus 3x plus 2, du would end up being 2x minus 3 dx. And the problem that we run into is I don't have up here 2x minus 3. I have 5x minus 7, and so I can multiply everything by 2/5. But if I multiply it by 2/5, I would get rid of the 5, so I'd end up with a 2. But 2/5 times 7 is never going to give me 3. So my pieces just don't line up correctly. So I kind of just run into a problem. Right? There's nothing I can do in terms of just substituting here. It's not a trig integral, right? It's not integration by parts. It's not a trig substitution because it's not one of those 3 forms. So I'm kind of stuck. So this is this problem. Oh, thanks. This problem is a good candidate for this thing called partial fractions. So, I'm going to write something here. So, Dr. Gorman does some fancy math. So if I could do some kind of fancy math, and I could turn that fraction on the left into the following, into the integral of 2 over x minus 1 plus 3 over x minus 2, then those I actually could integrate, right? So each one of those I could do a simple u substitution on. So on the first one, you know, if I let u be x minus 1, du is just dx. So I just end up with 2 over u. And so this first one would just end up being 2 natural log of x minus 1. And the second one's going to be 3 natural log of x minus 2. So if I could do some fancy math and get it into these nice 2 fractions, then I could integrate those 2 fractions because they're kind of easy to integrate. That's what partial fractions does. So partial fractions takes one fraction and breaks it up into parts, into multiple pieces of multiple fractions, that together those 2 fractions are the same as the first fraction. If you actually did this addition, you would see that it would actually be the exact same thing as this, right? So you'd have to multiply. If you did this addition, you'd have to make a common denominator. So the bottom part, x minus 1 times x minus 2, is in fact x squared minus 3x plus 2. And if you made that common denominator and then worked out what the top would be, you would get 5x minus 7. So so that's the basic general idea, right? Like, so that's the big picture that I want you to remember. We're going to start with some fraction. We're going to do some work. I'm calling it fancy math, but it's really not that fancy. It's pretty straightforward math. We're going to start with some fraction, do some math, get it into separate fractions, and then we'll just integrate the separate fractions because hopefully those are easier for us to integrate. So the big question is, how do I get those separate fractions? So getting those separate fractions is what's called doing the partial fraction decomposition. So you're taking this big fraction and you're decomposing it into smaller fractions. Okay, so steps for partial fraction decomposition. Okay, so when I am breaking down the fraction, I'm going to write down all the steps. The steps are kind of wordy. They may not make a lot of sense right this second. That's why we're going to do a bunch of examples. And I'll show you them, but I want you to have the steps in case you kind of want to like refresh what it is that we're doing. They're just ugly looking steps. So I just want to warn you of that, okay? So don't get put off by the steps. To write down mathematically what we're doing takes a lot of effort and it looks really terrible, but what we're about to do is actually not that hard. Okay, so that's the first thing I wanted to say. Okay, so in partial fraction decomposition, you have to be given some polynomial f of x over g of x. So f of x and g of x are polynomials. At the end of this section, I'm going to show you a problem that uses the technique of partial fraction decomposition, even though f of x and g of x are not polynomials. So I just want to kind of put it out there, like I'm stretching the truth a tiny little bit by saying like, oh, they have to be polynomials. They don't actually have to be polynomials, but for what I'm about to write down, they have to be polynomials. And I'll show you, like I said, that very last example. I don't think we'll get to it today, so we'll get to it next class. But in that very last example, I'll show you how to do partial fractions not with polynomials. Okay, So the first step is you have to make sure that the degree on the bottom is bigger than the degree on the top. So remember, the degree of a polynomial is the largest power in that polynomial. So the degree of g of x, so the bottom polynomial, has to be greater than the degree of f of x. So you might go, well, what do you do if it's not? And so you totally can still do the problem. You just have to do something first. Nobody likes what I'm about to say that you have to do first. But if it's not, you have to do long division first. So if not, do long division. So polynomial long division would be the thing we have to do first. Okay. The second thing that we're going to do is we are going to factor g of x. Well, that's good. I know some people don't like polynomial long division and some people do. So the next thing we're going to do is we're going to factor g of x. And when you factor g of x, you end up getting, like, well, I should say, when you factor g of x, you can get a lot of stuff. The things we're going to do partial fraction decomposition on by hand, when we factor g of x, our g of x might have factors that look like x minus some number to a power, right? And really, technically, x plus or minus some number to a power p. You might get factors that look like x squared plus bx plus c. You might get some of those raised to a power. You for sure could get x cubes and x to the fourth and x to the fifth. You could keep going, but the things we're going to work on are going to be polynomials of degree 1, so things that just have x to the first power, or polynomials of degree 2, so quadratics. You can generalize what we're going to do higher things, but it's so messy. It's so messy to do by hand. So we're not gonna do those by hand. Questions so far? And again, like I said, a lot of this is not going to make sense until we actually do a problem out. So the third thing we're going to do is 4 factors of the form x plus or minus some number to the power p. We are going to use the fractions a over x plus or minus the number plus b over x plus or minus the number raised to the first power plus c over x plus or minus the number raised to the second power. So we basically, we have to keep going all the way until we get up to the power p. So plus dot 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 plus, we'll just say q over x plus or minus a number raised to the power p. So for each of those factors, for each of those linear factors, we have to put just a constant number over top of our factor. And then we have to do it to all the powers as we march our way up to p. So for quadratic factors,
sorry, Dr. Gomez.
Yeah.
really quick.
Mm-hmm.
On the fractions that you just wrote down, aren't the first and second one the same thing?
Oh, yeah.
In terms of the denominator?
That should be a 2. This should be a 3. Thank you. Don't worry if you forgot long division. We're going to do a problem, so you'll remember long division. So then the quadratic factors are kind of similar, except on the top, we're going to make ax plus b over x squared plus bx plus c plus, dx plus e over x squared plus bx plus c to the second power. And again, we're going to do that same similar thing until we get up to, you know, whatever it is. So maybe it's, I don't know, wx plus y over x squared plus bx plus c to the z, or not to the z, to the p power. So basically for quadratic factors, we have to take the quadratic factor, raise it up until the power we get to. But on the top, rather than just simple variables, we have to have linear factors on top. So it's ugly. It's just terrible to write down what we're doing. So we're almost done, and then we'll do an example, and I think it'll make a lot more sense. So for part 5, we're going to set the sum of the fractions we need equal to f of x over g of x. So back equal to our original. And then finally, 6, we're going to solve for our constants. And then once we do all that, then we finally will be able to integrate. So it's kind of crazy because we have to do all this work before we integrate. And that's probably one of the biggest things that people do wrong in partial fraction problems is they do all the work, they find all the partial fractions, and then they go, okay, I'm done. You're not done. You have to actually integrate. So the reason we're doing this is so that we can make integration easier. Questions? No. Okay. So should we try some problems so you see what I'm talking about, so it doesn't seem like this is just really random stuff? Does anybody need me to wait before I go on to the next page?
Can you wait a second for me
Sure.
to write this down?
Sure. Yeah, that's why I was asking. Does number 4 say for, yeah, it says for quadratic factors. Yep, that's what that first part is. So, for quadratic factors.
Okay, I'm good.
Okay.
Thank you.
No problem. Anybody else? Yeah, so step 7 is basically going to be integrate. So do the rest of the problem. Yep. Other questions? No problem. Okay. All right. So, for example, integrate a. The integral 1 over x squared minus 5x plus 6 dx. So again, when you're given a problem, just because it has a fraction in it doesn't mean it's a partial fractions problem, right? So you want to look at it to be like, oh, could I just do a regular old U substitution first? But in this case, you can't. So it is going to be a partial fractions problem. So the first thing we need to do is we need to factor that denominator. So I have x squared minus 5x plus 6. So how can I factor x squared minus 5x plus 6? So x squared minus 5x plus 6 factors into x minus 2, x minus 3. So I have two different linear factors, and they're only both raised to the first power. So the fractions that I'm going to get are, so my original fraction, 1 over x squared minus 5x plus 6, we're going to need a over x minus 2 plus b over x minus 3. So if all of your powers are just to the first power, and they're all linear, you're just doing a constant over the first factor plus a constant over the second factor. If there were three factors, plus a constant over the third factor. It's only when stuff gets a little more complicated that we have to begin doing other crazy stuff. So questions about how I wrote down what that is. So basically I just did steps 1 through like 5, right?
Dr. Gorman, just to clarify really quickly, the A and B, those are just like arbitrary constants?
And we're going to figure out what they are.
Okay.
So they are going to have actual values, and we're going to figure out what those actual values are.
Okay, thank you.
So I got x minus 2 and the x minus 3 by factoring x squared minus 5x plus 6, right? So I'm looking for two things that multiply to give me 6 and add to give me a negative 5. So negative 2 times negative 3 is positive 6, but negative 2 and negative 3 is negative 5. Did I answer your question, Michael? No problem. Any other questions so far? No? Okay. So now what I want to do is I want to solve this. I have an equation. I need to solve it for A and B. The easiest way to do that is to clear the denominators. So if I think about multiplying this whole entire thing by x minus 2 times x minus 3, x minus 2 times x minus 3 is in fact x squared minus 5x plus 6. So that means that this first fraction just ends up being a 1. And this in the a over x minus 2, the x minus 2's would cancel, so I would have a times x minus 3. And in the b over x minus 3's, the x minus 3's would cancel, and I'd have b times x minus 2. So questions about how I got that? No. Okay, so you have a couple choices as to how you want to proceed from here. One thing you could do is you could multiply everything out and then equate like terms. The other thing is you could just pick creative values for x, which is the route that I usually go. Just because otherwise things get really, really messy. So if you notice, if we let x be equal to 3... and I plug that in here, I would have 1 is equal to a times 3 minus 3 plus b times 3 minus 2. So 3 minus 3 is 0. So we'd have 1 is equal to 0 plus b. So b ends up being equal to 1. Questions on what I did there? No. So what's another value that you think if I plugged in might be helpful in solving this? Yeah, 2. So if I plug in x equals 2, 1 is equal to a times 2 minus 3 plus b times 2 minus 2. So 1 equals minus a plus 0, or a has to be equal to negative 1. So now I found my values for a and b. So what that means is my original integral, 1 over x squared minus 5x plus 6 dx, is now the same as the integral of a, which is negative 1 over x minus 2, plus b, which is 1 over x minus 3 dx. Right, so I've now taken my original problem and I've broken it down into these nicer, littler integrals. Littler fractions, easier fractions, kind of however you want to say it. Questions? If you did the x minus 3 first and the x minus 2, your a was over the x minus 3, then your a would be 1. So whatever's with the x minus 3 is going to turn out to be a 1. Whatever's with the x minus 2 is going to turn out to be a negative 1. So yeah, it wouldn't matter the order you write them in. Other questions? Robert asked him about this. Oh, let me see. Oh, why is it negative 1 over x minus 2? So it's negative 1 over x minus 2 because a turns out to be negative 1, right? And so this fraction here is the same as these two fractions. So a is negative 1, so negative 1 over x minus 2, and b turned out to be 1, so 1 over x minus 3. Does that answer your question? No problem. Other questions? No. Okay, so now we're at a point where we can integrate this. Now, you could, for each of those little fractions, do a u substitution. There's another one of those like Dr. Gorman's shortcut tricks. It's not really my shortcut trick, but I'm going to call it my shortcut trick. I didn't come up with it. But we'll just call it Dr. Gorman's shortcut. If you are integrating, we'll say k, so some number, doesn't matter what it is, over x plus or minus m dx. So as long as you have x plus or minus some number, and it can only be a single x. It cannot be like, it can't be x squared. It can't be x cubed. It has to be x to the first power. This is going to turn out to just be k times the natural log, the absolute value of x plus or minus m. And you can, if you don't see that and you want to do the use substitution, that's totally fine. It's just a little bit of a shortcut to help us out here. So in this case, we happen to just have that. I just have an x to single power on the denominator. So this first fraction is going to end up being minus the natural log of x, the absolute value of x minus 2, plus the natural log of the absolute value of x minus 3, plus c. Calc 2 is kind of about sometimes like, oh, here's this integral that in Calc 1 I would have done use substitution, but in Calc 2 I'm a little more mathematically mature and I understand like what types of things give me natural logs, so I don't have to do a use substitution if it's obvious. So this kind of falls into the class of that. Like these are sort of obvious, so I don't have to go out and do the use substitution, but you definitely can, right? There's nothing wrong with actually doing the use substitution. So if you're like, oh, I don't want to remember that other thing, I would just do a use substitution. That's totally fine. There's nothing wrong with it. Questions? So it's not too bad, right? I mean, if you think of the grand scheme of the different types of techniques of integration that we've done, this one's like not terrible. This one just involves a lot of algebra. This first problem didn't have a ton of algebra. I mean, it had some, but it didn't have as much as some of the next problems we're going to do. Okay.
So that would be our
Sure.
final answer onto the
Yeah,
that would be our final answer.
Yeah. Now you can, like, I'm gonna leave the final answer like that. You can get more creative if you wanted to, right? You technically could rewrite this if you wanted to. If I put the positive one first, absolute value or natural log of the absolute value of x minus 3 minus the natural log of the absolute value of x minus 2 plus c. Remember, if you have the natural log of one thing minus the natural log of something else, this is the same as the natural log of x minus 3 divided by x minus 2 plus c. So you could work to make it look a little bit nicer, but there's no reason that you have to do that. I'm going to leave my answer just like this, and you guys are free to leave your answers like that too. Does that help?
Yeah, thank you.
No problem. Yeah, if the two natural logs were added together, instead of being subtracted, then yes, you would multiply them together. It'd be the natural log of the product. No problem. Other questions? No? Okay. So let's try another one. The integral of 5x squared plus 20x plus 6 over x cubed plus 2x squared plus x dx. Okay, so again, the first thing I'm going to check is my power on the bottom, is the degree on the bottom higher than the degree on the top? Yeah, so degree on the bottom is bigger than the degree on the top. We're good. We can just go straight forward. So now we have to think about factoring that bottom, right? So I have x cubed plus 2x squared plus x. So if I'm going to go about factoring that, what's one of the things I could do first? Yep, factor an x out. So x times x cubed, oops, not x cubed, x squared plus 2x plus 1. And then I need to factor x squared plus 2x plus 1. So what does that factor into? Yeah, so it's x minus 1 times x minus 1. Or not x minus 1, x plus 1 times x plus 1, or x plus 1 quantity squared. So this is going to be x times x plus 1 quantity squared. And so now I can do that partial fraction decomposition, right? So we're going to have 5x squared plus 20x plus 6 divided by x times x plus 1 squared. I'm just going to write it in factored form rather than the other form. And that's going to be equal to, so I have something over x, right? So we'll make that an a, plus, if you look down here, I have x plus 1, but it's showing up to the second power. So I need a b over x plus 1 to the first power plus c over x plus 1 to the second power. So you have to keep going up in powers till you get to the power that is on our fraction. So the power on this fraction happens to be a 2. Questions about that? No? Okay. I'm going to clear the bottom of the fraction. So we're going to multiply everything by x times x plus 1 squared. So on the left-hand side, I have 5x squared plus 20x plus 6. On the right-hand side, I have a times x plus 1 quantity squared plus b x times x plus 1 plus cx. So would use the most recent factor if there was a higher exponent. What do you mean the most recent, Kobe? Like if x plus 1 went to the third power, if x plus 1 went to the third power, I would need an x plus 1 squared, x plus 1 cubed in terms of my fractions. Is that what you're asking? Yeah, so in terms of making your fractions, you have to start at the first power and you have to keep going until you get to the highest power of that factor. And then here, I'm just really multiplying by that original denominator. So whatever that original denominator was, that's what I'm multiplying by there. Does that help? No problem. Any other questions? No. Okay. So we need to figure out what A is, what B is, and what C is. And we can get some of them using the trick we did last time by picking some nice values for X. So anybody think of a nice value for X that I could plug in that might make some things go away? Yeah, -1. So if we let X be equal to -1, we'd have 5 times -1 squared plus 20 times -1 plus 6 is equal to A times -1 plus 1 squared plus B times -1 times -1 plus 1 plus C times -1. So this is pretty nice, right? Because this piece goes to 0 and this piece goes to 0. So we're left with 5 minus 20 plus 6 is equal to minus C. So we have -9 is equal to -C. So C turns out being equal to 9. We okay with that? Is there any other nice values that we could use that might make some things go away? Yeah, 0 is another nice value. So, whoops, if we let x be equal to 0, we're going to have 5 times 0 squared plus 20 times 0 plus 6 is equal to a times 0 plus 1 squared plus b times 0 plus 1 plus c times 0. So in this case, b goes away and c goes away. And we have 0 plus 0 plus 6. So we have 6 is equal to a. And that's kind of the end of our nice values of making things go away. But I now know a and I know c. So the easiest thing to do from here is actually just pick another nice value. Even though it won't make anything go away, we can still figure out the b that we're missing. So what's another nice number that we haven't used yet? We've used -1, we've used 0. Yeah, so you could use any number you want. You could use 11 if you wanted to. Or Josh said you really only wanted 1. Yeah, so 1, but 11 would work too. So 1 is what I would pick, but you could pick 1, you could pick 2, like Sandra said. You could pick any of them, any number you want. If you really want to pick 100, you can. It's just, you try to pick a nice small number. So if I pick x equals 1, we get 5 times 1 squared plus 20 times 1 plus 6 is now going to be a times 1 plus 1 squared plus b times 1 plus 1 plus c times 1. Yep, you could pick 11,111 if you really wanted to. So in this case, we're going to have 5 plus 20 plus 6. So this left-hand side is going to be 31. Here I'm going to have a times 2 squared. So 2 squared is 4. So 4a plus 2b plus c. But I happen to know what a is and I happen to know what c is. So 31 is going to be 4 times 6 plus 2b plus 9. So 4 times 6 is 24, right? 24 and 9 is 33. So 31 is going to be 33 plus 2b. So if I subtract 33, I get minus 2 equals 2b. Divide both sides by 2. B equals -1. I added all that, right? 5 and 6, 11 and 20, 31, 2, 2, 1. Yeah. I don't see an arithmetic mistake. I have a positive one on my paper, but I just have written down what A, B, and C are, and so it's very possible I just wrote down the wrong thing. I don't see anything we did wrong. Questions? So obviously I'm out of room on this piece, like my little whiteboard here. So I'm going to write these on the next page. So let's take, oops. So, but this was our kind of original part here, right? That's where we were. So. Okay, so this is kind of where we were at. And then I just said that we had A was 6, so we found A is 6, B is -1, and C was 9, right? So that's what we just did on that last page. So we were looking for originally the integral of 5x squared plus 20x plus 6 over x times x plus 1 squared dx. And that is going to now be the integral, so a is 6, so 6 over x plus negative 1 over x plus 1 plus 9 over x plus 1 squared dx. And so the 6 over x, that's an easy integral to do. The negative 1 over x plus 1, that's another easy one using the trick. But 9 over x plus 1 squared, I need to use substitution. So I'm going to split these into 3 separate integrals. So we have the integral of 6 over x dx. I could write it as minus the integral of 1 over x plus 1 dx. Plus 9 times the integral of 1 over x plus 1 squared dx. And I'm going to do use substitution on that end integral. But so this first one, it ends up being 6 natural log absolute value of x. This second integral here ends up being minus the natural log of the absolute value of x plus 1 using my trick. But now I have to do use substitution on that next integral. So if I let u be equal to x plus 1, the innermost stuff, my du is going to be equal to just dx. So that's easy enough. So this is going to become 9, the integral of 1 over u du, or 1 over u squared du, which is going to be 9 times the integral of u to the minus 2 du. Oops. So this is going to be 9 u to the negative 1 over negative 1, which would be negative 9 x plus 1 to the negative 1. So that's what this last part is going to be here. Minus 9 x plus 1 to the negative 1 plus c. So when you do these, your integrals come out easier, but they're not always necessarily nicer. Right? You still have to sometimes, some of them you still have to do some fairly ugly stuff to them. Question. I think I've said this before, but integration is a lot harder than differentiation, right? So at the end of Calc 1, you can take the derivative of anything, right? We know how to take the derivative of every single function. There's not a mathematical function that you can make that we can't take the derivative of. Integration is a lot harder. This is actually the end of the techniques of integration. And so it is very, very, very easy for me to write down an integral that we do not have a technique to be able to integrate it. So you cannot integrate every function. And it's not even just like, oh, you guys are in Calc 2, you can't integrate every function. No, like mathematicians cannot integrate every function. So there are a lot of functions that there is no way to integrate them by hand. If you have limits of integration, you can always get a really good approximation for what that integral would be. But it doesn't matter. Like, yeah, even the people at MIT don't know how to integrate it. So not every function can be integrated, which is kind of crazy, since we can differentiate every single function we want, but we cannot integrate every single function we want. So it's just something to kind of keep in mind, that, you know, you can't always integrate everything you want. we will learn after the next, like, biggest chunk of stuff that we're going to learn on, like, so, like, right now we're dealing with, you know, techniques of integration. We will learn series and sequences, and you can integrate some functions by turning them into series. So there is a little bit more that you can integrate, but not a ton. And there you can integrate it, but your answer is in terms of an infinite series. And so is that really better? I don't know. But there's not always this nice little closed form for integrals like we have here. So just something to kind of keep your eye out on. Some people don't like series. I actually don't think they're that bad. It's just a matter of you have to get good at trying to figure out what you need to do on what series. But I actually don't think series are that bad. Other questions? Yeah, don't let other people scare you yet. Okay, should we try another one? You're all like, okay, you're going to do one anyway, so sure. Which is true. I'm going to do it. Okay, so I think this is C. Yeah, I think the last, we only did, yeah, A, B. This is C. Okay, so the integral of 2x cubed plus x squared minus 7x plus 7, all divided by x squared plus x minus 2 dx. So again, I'm given a problem. The very first thing I want to do is I want to look and say, so the power in the numerator is bigger than the power in the denominator. So I need to do long division first. So if you think about when you do long division with numbers, right, you put the top number underneath the little division box, right, and then the other part out in front. So we're going to do the same thing here. So the 2x cubed plus x squared minus 7x plus 7. It's going to go inside my division box. And then x squared plus x minus 2 is going to go outside. Okay, so long division of polynomials is all about comparing the first term of the divisor. So we're going to compare, in this first step, we're going to look at x squared, and we're going to compare it with 2x cubed, right? I'm not going to worry about all the other pieces yet. So what do we have to multiply x squared by to get 2x cubed? Yeah, 2x, right? I'm missing the 2, and I'm missing an x. So on top of this, I'm going to put 2x, and then I'm going to take that 2x, and I'm going to multiply it down. Just like in regular division, right? You put a number up on the top, and then you multiply it down. Same thing. 2x times x squared is going to give me 2x cubed. 2x times x is going to give me plus 2x squared. 2x times negative 2 is going to give me minus 4x. And then I have to subtract all of that. So subtracting, right, you need to distribute that minus sign to each of those pieces. So this becomes a minus. So we're going to be adding. That's a minus. This is now a minus. That becomes a plus. So 2x cubed minus 2x cubed goes away. X squared minus 2x squared is going to be minus x squared. Minus 7x plus 4x is going to be minus 3x. And I just bring down all the rest of the pieces, so plus the 7. So anything I did in that first piece that you guys are like, what?
Can you just go through it like maybe one more time?
So I'm comparing this x squared part with this 2x cubed part. So I look at them and I say, okay, what do I need to multiply x squared by to get 2x cubed? So I need the 2, and I only have 2 x's here, but I need 3. So that's how I got another x. And then I take this 2x. 2x times x squared is 2x cubed. 2x times x, 2x squared. 2x times minus 2 was a minus 4x. So that's what was in pink. And then I have to subtract it. So I'm subtracting it off. So if I subtract it, so I'm subtracting this whole thing. But basically what I did is I was like, oh, well, subtracting is the same as adding the opposite. So I changed all these signs to be the opposite sign. So this was positive, it's now negative. This was positive, it's now a negative. This was a negative, so I made it into a positive. And then these parts here, they go away because I have 2x cubed minus 2x cubed. Now I have x squared minus 2x squared, so I get minus x squared. I have minus 7x plus 4x, so I get minus 3x. And then I brought the 7 down. Does that?
Okay, so we pretty much distribute what the first component, whatever it needs, we distribute it into the divisor, and that's what we're subtracting off. Okay.
Yeah.
That makes sense now.
No problem. So now we're going to do the same thing again, right? So now I'm going to compare minus x squared with x squared. So what do I need to multiply minus x squared, or what do I need to multiply x squared by to get minus x squared? Okay. So yeah, so it's just the -1 because I already have the correct powers on the x's. So I have 2 x's on my divisor, and then this part I'm trying to divide into already has 2 x's. So it's going to be a -1. I'm going to take that -1 times each of those pieces. So we're going to have minus x squared minus x. -1 times -2 is a positive 2. And then I'm going to subtract them. So minus. So subtracting is the same as adding the opposite. So this is going to become a plus, which means this is a plus, this is a plus, and this is now a minus. So x squared minus x squared, or minus x squared plus x squared is 0. Minus 3x plus x is minus 2x. 7 minus 2 is plus 5. Are we okay with that? Yes. Okay, so now the thing is that I want to take the, if you look, I have a minus 2x, and here I have an x squared. So since my power down here is smaller, I'm done. I can't do any more division. So my integral now becomes, this fraction here now becomes the quotient 2x minus 1 plus the divisor minus 2x plus 5 over or the remainder, minus 2x plus 5, over the divisor, x squared plus x minus 2. And those first two pieces, I know how to integrate those, right? So this is going to be equal to, so what's the integral of 2x? Yeah, x squared. So we're going to have x squared minus x plus, now I have the integral of minus 2x plus 5 over x squared plus x minus 2 dx. Right? So I was able to integrate those first two pieces because I just know how to integrate them. And then now I'm left with this fraction piece. And so now on this fraction piece, we're going to do partial fractions. But before we do that, questions about anything I've done so far? No. Okay. So I'm going to take this to the next page just so that we can... Oops. Okay. So, all right. So we've got, right now, we know the integral we started with is now equal to this x squared minus x plus the integral of minus 2x plus 5 over x squared plus x minus 2 dx. So on that fraction part, we're going to do partial fractions. Now is the case that my bottom degree is bigger than my top degree, and I need to factor that bottom. So what does x squared plus x minus 2 factor into? X plus 2 times x minus 1. Great. So x plus 2 times x minus 1. Excuse me. So now we're going to take this minus 2x plus 5 over x plus 2 times x minus 1. And we're going to break it up. So I just have two factors and they're just linear. So this is just going to be a over x plus 2 plus b over x minus 1. Are we okay with that? Yes. Okay, so I want to do like we did before. We want to clear the denominators. So x plus 2 times x minus 1. So we have minus 2x plus 5 equals a times x minus 1 plus b times x plus 2. And then I need to pick values for x. So what's a nice value for x that'll make some stuff go away? Yeah, so 1. So x equals 1. So I have minus 2 times 1 plus 5 equals a times 1 minus 1 plus b times 1 plus 2. So 1 minus 1, that's going to go to 0. So we're going to end up with negative 2 plus 5 is 3, is equal to 3b. So b is going to be a 1. Oops, well, that's fine. B equals 1. And then, yeah, the other nice value we should pick is negative 2. So negative 2 times negative 2 plus 5 is going to be a times negative 2 minus 1 plus b times negative 2 plus 2. So the second part here is going to go to 0. So I've got 4 plus 5, so 9 is equal to minus 3a. Divide both sides by negative 3. A ends up being equal to negative 3. So my original problem here is now going to be x squared minus x plus a, which is negative 3 over x plus 2, plus b, which is 1 over x minus 1 dx. And then those are both nice ones to integrate, right? So this becomes x squared minus x minus 3 natural log of x plus 2 plus natural log of x minus 1 plus c. Kind of ran out of room with my plus c there. Questions? guys don't have any questions? You're very questionable.
Dr. Gorman.
Yeah.
I think I just missed something on the. So the top right of the screen where it's x squared minus x plus the integral.
Mm-hmm.
How did you get that? I probably missed it.
How did I get like those, like the integral part or the whole thing, or?
How did you? Let me see. How do I phrase this? Well, how did you get that integral on the last part? I'm probably missing something small.
Okay,
But-
so are you okay with this part here? That I copied this part from the other page.
Yeah.
Okay, so I now took this integral, minus 2x plus 5 over x plus 2 times x minus 1, and I broke it down into these two small fractions, right? A over x plus 2, b over x minus 1. And then I found that a was negative 3 and b was 1. So this part here would be negative 3.
Plug and play.
And this would be 1, right? And so that means is this, the integral of this big fraction breaks into the integral of these two littler fractions. Does that help explain?
Yeah. I was I don't know, I blanked out or something.
No, that's okay. It's a lot of algebra. It's a lot of steps, right? And it's hard too because usually when I do these problems, they do take a whole board. Like in a classroom, they take a whole board up. But then at least all the pieces are on at one place, right? And so that's kind of the downside here is that it took 3 pages, which equivalent to how much board space I usually have. However, we don't have, like, you can't see it all at once. So it's kind of unfortunate. But the way it is.
Okay. Well, it did make sense, so thank you.
No problem. Any other questions? No. Okay, so I do have more examples. I have 3 more examples that I want to do. 2 for sure, but probably even the third one. However, my next example, which is really the one I want to do next because it's one of the ones that has those quadratics in the bottom, which we haven't seen any of those yet. It's just too long to do in 16 minutes, which is what we have left in class. I mean, I could do it if I rushed through it, but I'd rather not rush through it with you guys. So why don't we stop there for the day, and then I will do those next 3 examples next class. But if anyone has any other questions they want me to answer or anything like that, I'm more than happy to do that. Otherwise, you can have a good day. Enjoy your long weekend. I know it doesn't get you out of math class, but...
Thank you, Professor.
No problem. Have a good one. No problem. You too. Yeah, the college is closed Monday, so nobody should be holding classes on Monday, for you. So on Monday I will not have office hours because college is closed. But I'll have office hours on Tuesday and Wednesday and Thursday of next week.